this third week, we will be focusing more on signal analysis. Like you already know by now, CBM, everything actually depends on our analysis of this signal. So, by signal I mean the information which has been received by the transducer, put on the machine, it has been acquired and converted into certain values and stored in a computer. I will talk about the conversion part later on, but the signal per se, which is nothing but a function of time, certain information, be it in the form of voltage or anything. So, this is a signal. So, in this class, we will focus on what are the different time domain analysis and how this time domain analysis is done for a signal. Okay. So, to begin with, you all have a good idea of what signal is. It is basically something which is conveying information. Okay. And in CBM, we are actually using a transducer, okay, which is measuring certain mechanical quantity in our case could be vibration, and then transducer is giving some voltage signal with as a function of time. Now, this signal, I will come to the different types of signal later, but then I must tell you in CBM we do what is known as the signal analysis. So, basically I have a machine, put a transducer, get a signal. By analyzing the signal, I would be able to tell what is the defect in this system, as opposed to those who are in the areas of controls, they would know what is known as system analysis, wherein I give a known input to the system in terms of an excitement or excitation, I measure the response. So, the response by the input is sometimes what is known as the transfer function or the frequency response function. So, this ratio gives knowledge about the system. By system I mean lets us know what is the natural frequency of the system, what is the damping present in the system, and so on. So, this is something which we are not going to focus in CBM, rather we will focus more on this signal analysis. Okay. And when people do experimental model analysis, they do what is known as give a known input and get a output. So, this output by input is a transfer function, and from the analyzing the transfer function, they can find out the natural frequency. In our case, we measure vibration. Had I known the input, my machine would never have been having any problem, because I would have made sure that this excitation does not happen. So, we are kind of doing an inverse problem in the sense we are measuring the vibration. From there we are trying to find out what could be the possible causes. Of course, nowadays there are many model based diagnostic techniques wherein people develop nice mathematical models, validate them with experiments, and once the model is well built, as I was telling you in the previous classes of predicting the remaining useful life, if a good model is there, we can predict the remaining useful life of that machine. But we are left with something as signal. So, signal can be constant with over time. Okay. So, this is what is known as a constant, like a DC signal, or what is known as a static signal, as opposed to a signal which is varying with time. This is a dynamic signal or an AC signal, alternating current signal. Okay. So, our objective is to find out the features of this signal, as opposed to another classifications I must do at this time, which is known as a stationary signal or a non-stationary both are alternating signals or dynamic signals, but their characteristics has a difference. For example, if I plot with over time a stationary signals, this pattern is going to repeat. Whatever I can draw here, you can see this pattern is repeating at all times. So, this is a good example of a stationary signal, as opposed to with a different pen. If I am drawing a signal which happens once and that is it. So, if I take a time t, another time t, another time t, the characteristics of the signal at different time 1, 2, 3 are not the same, unlike this one, wherein the characteristics are the same. Okay. So, this is an example of a non-stationary signal. Though both the signals are dynamic, that means they are changing with time, but the features are not the same at different instances of time, and that is a non-stationary signal, as opposed to this being a stationary signal where the features are the same. So, we find out in signal analysis response of a vibrating system due to unknown excitations. If this excitation was known, I would have been having a nice machine, because I would have taken efforts to remove this excitation. But excitation occurs only because there is a defect which has happened in this machine because of various reasons. Okay, could be poor design, could be lack of lubrication, could be wrong commissioning, wrong installation, wrong operations. Okay, so there are many reasons why these excitations occur, but it is this signal which I see in the time domain, which has been measured from this motor with the transducer. Okay. And later on we will go into frequency response of this signal. So, every peak here corresponds to a particular component here. Okay, but then that is something we will discuss in the next lecture. But even in the time domain, many features can be measured, can be analyzed, so that they give us some clue as to what is wrong with this machine. And for the sake of completion, I will just mention to you on modal testing being done through what is known as the system analysis. It is this output by input, response by excitation. So, the frequency response function shows the inherent properties of a dynamic system, which is independent of the excitation force and type. So, signals, I had explained you what a stationary signal is, what a non-stationary signal is. So, some are deterministics, like this periodic signals, because one signal here is related to the speed of this. One can relate to this, that is a deterministic signal, whereas this is a random nature signal where there is a raindrops falling on this, and this is continuously if you are hammering it. This is a non-stationary signal, because this each time our hammering occurs, there will be a spike in this signal level, and they are continuously hammering, unlike if you have hammered it once, it is a transient. So, this signal analysis can for all these different signals, a deterministic stationary signal, a random stationary signal, a continuous non-stationary signal, or a transient non-stationary signal, there are certain features in the signal which will characterize the signal better, and that will help us understand the condition of our machine. Just to give you another feel, this signals which we hear, typical sound and noise signals, somebody raindrops falling on an umbrella, okay, hammering, okay. So they all have different frequency characteristics. Gearboxes, a lot of frequencies and sidebands around frequencies. Random noise means many frequencies at a high level are getting excited and so on. So we will see the different frequency characteristics later on when we talk about Fourier analysis. But these signals, a lot of features can be measured and found, which will help us understand the signal better. For example, a deterministic signal is very easy to understand from this. The frequency of this signal, okay, this is the time, and from the same time I see that two take the time over here, actually you will see for the same time this frequency in this wave there are two complete waveforms, whereas there is one complete waveform in this case if the line is put here. So this one is a single frequency signal. Frequency is nothing but inverse of the time period. Same is true here, frequency is inverse of the time period, but the time period here is shorter by half of the earlier time period. So the frequency of this signal is higher. So low time period, high frequency. So time and frequency always have an inverse relationship. That is an universal truth. Nobody can deny that. Okay. But then when I add up all these two signals, I get both the signals. Okay. So if you add many such signals, you see all these blue signals which are there of all of different frequencies and amplitude. If I add them up with infinite terms, in fact, I will land up with this green square waves. So these are nothing but the harmonics of the fundamentals, all these green signals, F0, 3F1, 5F1 and so on. Similarly, for a sawtooth signal, they all can be broken up into sums of different sines and cosines and so on, which we will see in Fourier series. So a signal which is time varying can be represented as infinite sums of sines and cosines. Another thing I must tell you with example of sound, I am just telling you about a sound wave. Sound wave in air is a longitudinal wave. So there is compression. So there is an increase in the density, rarefaction, decrease in the density, and this is responsible for the pressure waves propagating from one end to another. So this speed at which this wavefront moves is nothing but the speed of this sound, that is 344 meters per second. Of course, the particles themselves do not move, they always oscillate about their mean positions, and that is what is known as the particle velocity or the vibration velocity. And these waves can be of many form, and this is just a longitudinal wave. Just for demonstration I have written here. So the wavelength and speed of sound, there is again a relationship that c is equal to f times lambda. Okay. So higher the wavelength, lesser is the frequency. Okay. And smaller the wavelength, higher is the frequency. So this is universally true, and for the case of air at room temperature and normal pressure conditions, it is 343 meters per second in air. Speed of sound in water, it is 1500, in steel it is 5000 meters per second. Just some idea, you must keep this handy, whenever we are doing diagnostics, you will see that this relationships, helps you understand some of the physics which we will discuss later on. So, we had already discussed this by this is obviously a high frequency signal. So, all of you must develop an eye looking at an oscilloscope, and it comes with a lot of practical experience. Looking at a signal, you should be able to tell whether it is high frequency and low frequency, okay? Because many phenomena are related to the frequency of the signal. So, this is a low frequency signal, this is a high frequency signal in the same time steps. Okay, so, this kind of visualization of a signal helps you later on realize, because when you many times when you do time domain analysis, all you do is have a machine, put a transducer and get a signal. So, this signal you can see in an oscilloscope. Even in the time domain. Okay. So, you all must, as a prerequisite, I am sure all of you who are taking this course must have had an experience with an oscilloscope, just a device to represent an analog time domain signal. By the way, these are all analog signals. I will talk about digital signals later on when we do talk about digital signal processing, okay, after we talk about computer data acquisition. But these signals can be seen or visualized in an oscilloscope. So, this is typically the frequency characteristics of a random signal. By random signal, I mean all frequencies are present at a certain amplitude, of course, beyond a certain cutoff frequencies. When we have an impulse like a missile getting fired or something hammering, it is an impulse function. So, an impulse function in the frequency domain will look like this, wherein this is the flat part of the spectrum. Of course, this frequency range depends on the duration of this impulse. I will just relate this with an example which I do in my class. I am not sure whether I can repeat that here, but all of you will experience that if a peak is very sharp in the time domain, this will boil down to very high frequency signal. For example, two metals, I do not have two metals here, but two metals striking against each other, that metallic ting ting noise is a very high frequency noise, because the time duration of impact is very, very less. But if I have two very soft, this is very soft, okay. This is relatively soft compared to a metal, okay, and the noise is little low frequency. So, that means if the impulse is very, the time duration is very large, this gives rise to a low frequency signal. So, wherever you have impacts occurring, things falling in machines, dropping. So, they will if there are metallic compounds, you will hear a lot of impacting metallic noise which are high frequency, as opposed to something falling like a thud in a very damped environment. You will have a large time period, so low frequency signal. Just keep that in mind. Now, qualitatively, we have got a feel of the signal, high frequency, low frequency, how they look, how they sound. But then there are many features of the signal, okay, which can be measured, okay, from this signal here, certain definitions. One is this is the green one is the signal, which could be a sine wave. In fact, it is a sine wave. So, the peak amplitude is from the 0 line to the maximum is the peak amplitude of the signal, and then the peak to peak is twice of the amplitude. the RMS value is given by this expression. If you do it over a time period t, okay, you do this integration and then square it and then integrate it, divide it by the time period and take the square root. So, an RMS value of the signal actually conveys what is the energy in the signal. For example, if you look at a signal which is, and the average value is something like this, arithmetic mean. So, this signal, if you look at a sine wave, its mean value is 0, but that does not mean that it is not conveying any energy. The RMS value is a true representation of the mean of the signal, because all the negative quantity here will actually get nullified if you square it. So, RMS that way has an advantage that you can find out the true energy in a signal. And the crest factor of a signal is given by the peak value of the signal divided by the RMS value. In fact, there are many features of the signal even in time domain which could be calculated. But one thing if you notice here, to do this integration, I need to have the value x t dt. So, this x t has to be given to me in a mathematical form, okay, to do this integration. This is good for when x t is equal to a sin omega t. I am sure all of us must have done this in our first year electrical circuits course. But in a real world machinery, the problem lies that signal looks like this, and I possibly cannot define it with a mathematical signal. I do not have it. This is not known to me. So, how do I go ahead and do this computations or do this integrations? So, in that sense, later on we will see that each of the signals could be made out of a series of xi, and I am sure if I give you this signal, not the mathematical waveform, but this series of numbers as xi, all of you could use popular software like Excel, MATLAB, etc., to find out the mean value of the signal or the RMS value of the signal. So, later on we will see how from an analog signal we can get the digital values xi of the signal. Okay. So, signals always will not be sine waves. In fact, real world signals are this, and the challenge is I do not have a mathematical expression for x, which I had already told you. So, if you look at the time domain descriptors of the signal, okay, all these quantities are given in xi. So, if you see the mean, maximum value, mean value, range of the signal, sum of the signals, RMS values, standard deviation, variance, kurtosis, skewness, crest factor, form factor. So, for any given signal given to me as an array x I, I can compute all these features digitally, and later on you will see in a digital signal processing, even in the time domain, all I do is this array xi. So, I can do all math operations on this. It all depends on my algorithms which I am going to use. Okay. So, how? So, we can all program this, or somebody has to give me xi, and that later on we will see the technique called computer aided data acquisition, how this xi can be obtained from a signal xt. So, once xi is known to me, all these features which I have described here in this table, xi, maximum, minimum, range, sum, RMS values. So, this integration has been replaced by a summation over n values. Similarly, the standard deviation, variance, kurtosis, Q-ness, okay, rest factor, form factor, and so on. But always the time domain analysis is not sufficient, because every mechanical component has a characteristic frequency or frequencies, and signature of a machine component is unique, and that is why from the time domain analysis we will move to the frequency domain analysis. And this is true both for stationary and for non-stationary. So, we will talk about frequency domain analysis both for stationary signals and both for non-stationary signals, and how this can be done. Just to give you an idea here. So, this is a 10 hertz pure tone. How can I say that? Well, this is a, if you look at the time period here, it is 0.1 seconds. So, inverse of 0.1 is 10. So, that is 10 hertz. So, for a pure tone, just measuring the time period, now I am sure many of you would have already done this in your electrical lab experiments and oscilloscope. I can take the inverse of the time period and find out the frequency. And as rightly told, 10 hertz corresponds to the amplitude 10 here in the spectrum. But when I sum up two sines, it is very difficult for me to look at this time domain and tell what are the frequencies and what are the amplitudes. But then if I go to frequency domain, I can say, well, that sine signal which I showed you here basically consists of a 10 hertz 10 amplitude sine, so 10 hertz 10 amplitude sine wave and a 5 amplitude 50 hertz sine wave summed together. Okay. And some other time periods you will see when the frequencies are close by, okay, I will see the amplitudes increase and decreasing, and this is the phenomenon of beating, which you will hear and analyze later on when you talk about signal beating and heterodyning. Okay. So, we will focus subsequently on stationary signal and non-stationary signal, and as you know, in any machine there are moving and fixed parts in machine, rotating parts, reciprocating parts. So, all of these parts, when they rotate, they are responsible for generating signals which are varying with time, and it is this time varying signals which we have to analyze in time domain, in frequency domain, in time frequency domain to find out what are the possible faults in the systems. Okay.